All right, so we're going to go over the review questions first and then do practice problems, push through those over the next couple days. Like I had down for bell work. Are we good now? Or gooder? Gooder. We're gooder. All right. Go over the review questions and practice problems. I don't have a lot of slides for the review questions. I'll just have this as a placeholder because most of these are just question answer. Either you know them or you don't. And remember, review questions are conceptual. So usually it just means reading that section in the book again and pulling out information that you need to answer the question. So the first real slide we're going to have is an until practice problem number 1. So we'll just leave this placeholder there for the review questions for now. We should do this kind of as a game. I was going to get a beach ball, use a globe, but maybe we'll do something a little less. Here you go, Zach. We'll just you get to hand it off after you answer the first question. Before we do the second question, we'll just keep doing them in order. That way, it's not just the same person answering every question. And don't mean to highlight if you don't know something, but if we need help answering it, this is a good thing to discover now what you weren't able to maybe uncover in the text or from the notes before the exam. So, what is the difference, Zach, between? And I'm going to stop using names. Just sorry about that, but I may forget to edit that out of the YouTube. But so I might just look to whoever has the wipes and ask you for the answer. Okay, so as not to keep your name continually being put out there on the internet. So what's the difference between the continuous theory of matter and the discontinuous theory of matter?
The continuous theory is the substance composed of long unbroken blobs of matter, and the discontinuous is perhaps matter was not really continuous, and when he magnified it, you couldn't really see the individual cells.
Right. So I'll tend to go through and listen to your answer and then maybe read the book answer, so it helps. You hear it twice. You hear it from your peer, and you hear it from the book, and then we can talk about it if there are any questions. But the continuous theory of matter states that matter comes in long continuous sheets, long continuous pieces, if you will. The discontinuous theory, however, assumes that matter comes in little packets, and the only reason that it looks continuous is that we cannot magnify it enough to see the little packets of matter. So there's packets there, but they're so small that we just can't get down to that level. We can visualize it by saying Frizzle's school bus and go there, right? To be able to see that small. But frankly, we don't have anything, even with our incredible technology of today, that can actually do that. We talked about the electron microscope, and a lot of people say, oh, look, I'm looking at an atom. No, you're not really. You're looking at an image that's created using fluctuations in current fed into a model that approximates what we think it looks like. That's not the same thing as a picture. Okay, go ahead. Just you can pass that off so people can look at their next answer in advance. So we'll go ahead and say now that this is going to be number 2, but why don't you go ahead, B, and pass it so the number 3 can be thinking while you answer number 2. All right. Number 2 says, what 2 laws were instrumental in the development of Dalton's atomic theory?
The law of mass conservation and the law of definite proportions.
Yes, the law of mass conservation, law of definite proportions. Remember he said matter cannot be destroyed or created, it can only be rearranged. And that the law of definite proportions say that in a certain compound, if you have this element and this element, certain numbers come together, there's going to be definite proportions. There's going to be the same proportion. Like, so if it's by mass, I've got this much and this much. If I have a different mass, it's going to require a proportional same amount, you know, those definite proportions. So a certain amount of oxygen, a certain amount of hydrogen, if I'm making the same compound, they always combine in the same ratio. And we know that the masses combining in that ratio, eventually we're going to learn that, you know, or we have already learned, that it's not just simply the masses, it's the actual number of atoms. So they always combine in a certain proportion. Water is always 2 hydrogens and 1 oxygen. If it's not 2 hydrogens and 1 oxygen, it's not water, it's something else. If it's H3O, for example, it's hydronium, it's heavy water. It's something different. Okay? And Dalton's theory became so influential because he not only explained mass conservation and explained definite proportions, but he also predicted what was later discovered to be Multiple proportions, right. So that if, anyway, don't want to get necessarily too deep into all that stuff right now, but just for right now, those are the two laws. He explained conservation and definite, and he predicted multiple. Okay? Number 3. And the question is, describe how the law of mass conservation can be explained using the results of experiment 2.1, which we did not do, right? So you had to read it, and I said skip it, didn't I?
Yeah.
So we're going to move on to, since now we're going to keep that answer and say, list, or the person, list the 4 assumptions of Dalton's atomic theory. You don't know them off the top of your head? You got to read them?
All elements are composed of small indivisible particles called atoms.
Mm-hmm.
All atoms of the same element have exactly the same properties. Atoms of different elements have different properties, and compounds are formed when atoms join together. Since atoms are indivisible, they can join together only in simple whole numbers.
Right, and it's straight from the book. Okay, those 4 points. How are you going to remember it? Atoms, same, different. And then, for the last one, discrete whole numbers, right? They come together in simple whole number ratios. So, atoms. Just the fact that there's such a thing as an atom, that, discontinuous theory of matter, that there's a small packet of something, matter. So, building blocks, atoms. That's Dalton's 1. Second, atoms of the same element behave identically. So it's not based on our mood or our feeling or the temperature, but atoms behave like atoms. Now, they are affected by temperature and pressure and those kind of things, but every atom of that same element behaves the same under those same conditions. That atoms of different elements behave differently because they're not the same, so they behave differently. And that lastly, that atoms are indivisible. You can't take half an atom, okay, when you bring these things together. So when they come together in whole ratios. It's not 1 to a half. It's always 1 to 1, 1 to 2, 1 to 3, 2 to 3, some combination of whole numbers. You can't have half of an atom in a compound. It has to be a whole number. So, which of those are technically wrong? Technically, not for the scope of this course, but technically. Ma'am? 1 and 2, so that we say that elements are made up of atoms and atoms cannot be divided any further, but we know we can split the atom, but the result is pretty dramatic, and we're not going to do that here in class. And that all atoms of the same element have exactly the same properties. We know that's not true, and we'll find out more specifically when we talk about the makeup of the atom. And what we're dealing with there is, in the nucleus, there are subatomic particles called neutrons that have mass, but they don't affect reactions at this level we're going to get to in any major way. So we're going to learn later on that an atom has its name, whichever element it is, based upon the number of protons in the nucleus. Protons determine what it is. Neutrons do not. Electrons do not. Protons do. If you change the number of protons, you've now created, or now you've not created a new element, you've changed the element into another element. Okay. We are on number 5, and 5 is a structural question. Hopefully you were able to follow when I talked about this in class, the difference between, and I'll do 5. Okay, we'll talk through 5 together, and then if that's okay, unless you're prepared, you want to talk about it?
You can talk about it. I mean, I have the answer, but you can.
Okay. Well, what's the difference? Why don't we dialogue a little bit here? What's the difference between an atom and an element?
Well, I just have that an atom is what an element is composed of, and an element is what a group of atoms compose.
Right. So we have an atom of an element. Elements are made up of atoms. They're not compounds. They're individual atoms. So to have an atom means that you've got one piece, one smallest packet of an element. And if you have a sample of an element, you have a sample of atoms. Why? Because it's an element. It's not a compound. It's a pure substance. Okay, now that we've got that vocabulary. So atoms are the smallest packet, the smallest structure. That is what an element is made up of. One packet of an element is an atom, and when you have a sample of an element, you have a handful of atoms. Okay. What difference between a molecule and a compound?
I don't know if this is right, but a molecule groups itself with other molecules to form a compound which is composed of multiple molecules.
Close. A molecule is a structure made up of atoms. Okay? So they're the same. An atom is to an element as a molecule is to a compound. An atom is the smallest grouping, the smallest size of an element. That's an atom. A molecule is the smallest size grouping for a compound. So what they appear to be, the structure, the name of the structure for an element is atom. The name of the structure for compound, or for a molecule, or excuse me, the name for an element, the structure is an atom. For a compound, the structure is a molecule. Okay, so it's the difference between what is it and how was it made. An element is pure substance made up of atoms. A compound could be a pure substance if they're all the same molecule. Okay? But here's the deal we'll learn later. Just like you make a molecule by putting atoms together, okay, you take atoms together to form molecules. That's another way to say this is you take elements to form compounds, right? But the structure of an atom, take those structures together, forms a structure of a molecule. So the difference between an atom and a molecule?
An atom is a complete piece of an element, while a molecule is only part of an element. I don't know.
Okay, so here's the deal. An atom is a structural piece that come together to form a compound. If I'm going to make a compound, I need to take elements and build up the compound to create the compound. And it works the other way. An element and a compound, I just use the phrases interchangeably. Here's one of the problems. To speak of an atom or an element, at some point they're the same thing kind of in the mind. And to speak of a compound and a molecule, they're kind of the same thing in the mind, right? So I might occasionally at times say, if you take these two elements to form this compound, or these two atoms to form this molecule, I'm talking structure to structure and nature to nature. But sometimes it'll cross-speak. I'll take two of this element to form this molecule. You know, it gets confusing at times, I understand. Let me go ahead and, for our help, I'll read straight from the answer key to see if this helps clarify it for you. But it's a matter of talking about what the nature of it is and what the structure of it is. That's the hook. So elements are made up of identical atoms. That's for A. Compounds are made up of identical molecules. An atom, this is C, an atom is the smallest unit of matter. A molecule is a unit of matter, but it's formed when atoms come together or join together. So a molecule is made up of more than one atom. And elements are made up of identical atoms. Compounds are made up of identical molecules. So if you think in terms of maybe a helpful way to think about this is when I'm talking about an atom, I'm talking about one of them. When I'm talking about an element, I'm talking potentially about many of them. Maybe that's a way that'll help us transition, okay? An element is made up of atoms. When I have an element, now when I say I have an element, in my mind that could be one atom of it, 10 atoms of it, and a bazillion atoms of it. I have an element in my hand, okay? But whatever it is, the element that I have in my hand, no matter how many of the element I have, the smallest piece is going to be an atom. Because elements are made up of the construction of atoms. If, however, in my hand I have a compound, compounds are made up of molecules. Molecules are made up of atoms, okay? But if I have in my hand sodium chloride as an example of a molecule, if I have one molecule, or I have 10 molecules, or I have 100 molecules, I still have the compound sodium chloride in my hand. But the compound is the smallest structure that it exists as. If I take the smallest structure of a molecule, Okay? If I take that compound, its smallest structure is a molecule. I can break that molecule up, but when I break it up into atoms, which means I now have elements. Okay? So, atoms of elements come together to form molecules of compounds. Atoms of elements come together to form molecules of compounds. If I say I have an atom of zinc, I have one zinc atom. If I say I have the element zinc in my hand, I have multiple atoms of zinc in my hand. I could have one, but I could have more. If I say I have the compound sodium chloride in my hand, I could have one molecule or a bazillion molecules. But the smallest structure is one molecule of sodium chloride. And if I want to break that down even more, when I take a molecule, I break the molecule into atoms. And if I break the atoms, I blow up the school. Okay, so that's kind of the difference between the terminologies. Atom, an atom is the smallest structure of an element. A molecule is the smallest structure of a compound. Compounds are made up of elements because molecules are made up of atoms. Number 6, where are we at? Are you answering or are you passing for 7 now? Okay, want to pass and then we'll talk about 6? Okay, what are the physical characteristics that distinguish metals from nonmetals?
Metals have luster, easily shaped, and can conduct electricity, but nonmetals are brittle and cannot conduct electricity.
Okay, so metals, nonmetals. Metals are going to be one, and the nonmetal is going to be the antithesis, the other side of that, right? So the first one you mentioned there was malleability. Was that right? Can shape it? Or did you do? Okay. So if you can shape it, the term we used was malleability. Metals are shapeable. Metals are malleable. It means if I take a metal and put it on an anvil, I hit it with a hammer, it changes its shape. I bend it. Which means if nonmetals are the other, what does that mean? If they're not malleable, they're brittle. So metals I can shape, malleable. Nonmetals, generally speaking, they shatter, so they're brittle. So if you can bend it and shape it, it's a metal. If it breaks in your hand and crumbles, it's a nonmetal, generally speaking. That's the kind of physical characteristics we're looking for. If we have to have this either or, that's what we're talking about. Now we do have metalloids. They're right in the middle. They kind of act like both at times, and we're not getting into all that for the scope of this class. For this class, it's either metal or nonmetal, which means it's either shapeable if it's a metal, or it's not shapeable, it's brittle if it's a nonmetal. The second one you had was luster, right? Takes a shine. Metals take a shine. I can buff up a metal. I have to, years at the Naval Academy, buffing up my belt buckle, things like that, making it shiny, shining up your shoes. No, shoes not a metal, but the point being that the metal belt buckle takes on a nice shine, and that ability to take a shine is because of the luster, that's the term we used, luster, of the metal. Nonmetals don't have luster. They're non-lustrous, right? You don't go and take a chunk of calcium and try to buff it up to make it look pretty. Well, actually calcium's a metal, so that's a bad answer. But let's go to the other side. Take one of those other elements on that side. You don't bother to buff them up because they don't take on a shine. And the last one you talked about was conductivity, right? So metals conduct, nonmetals don't, which is why we have copper wire, not sulfur wire, right? First of all, it'd stink in your house if it ever warmed up, but besides that, a chlorine wire or something like that. Well, part of it is phase. It has to be a solid at room temperature, but the other point is you have metal in a wire because the metal will conduct electricity. That's the purpose of the wire. So malleability, luster, and conductivity are the attributes of a metal. Nonmetals are brittle, they lack luster, and they're non-conductive. So, all right. Number 7. 7 reads, how do you determine whether an atom is a metal or a nonmetal from the periodic table? Whoever has it. Yep.
I gave it to her. She's next. Oh, yeah.
Yep. So you're 7, she's 8.
It's left of the jagged line.
Left of the jagged line, it is a metal, and right of the jagged stair step, it is a nonmetal. Are there any exceptions? That's the second part of the question. Are there any exceptions to that rule?
I mean, you got your metalloids, but that's beyond the scores.
Okay, we talked metalloids, yeah. Is there another exception?
Helium, or not helium, sorry, hydrogen.
Hydrogen, yep. Hydrogen's the exception. Hydrogen lives out of its territory. It's the whole Romeo Juliet or West Side Story thing, you know. She's supposed to be over there, but she's staying out over here with the wrong crowd. So hydrogen technically is a nonmetal, but resides on the metal side of the jagged line on the periodic table. And I mentioned before that part of that is because, technically speaking, the most appropriate way for us to visualize the periodic table is not as a flat sheet, but more like a globe, more like a cylinder. Okay? And we're going to learn properties later on that, for example, potassium, there are certain characteristics of potassium where it is most close to calcium and argon. So for certain characteristics, it would almost be appropriate to have the periodic table as a straight line, but that would take up the whole wall and be a real thin border, right? And then for other characteristics, other things are true. So one of the best ways to visualize the information we have here, that it means something when something is above or below, and it means something when something is to the left or the right. But if you think about it, as you go across the table to the end, you should technically wrap right back around down one row. And so if you were to take the periodic table, curve it around like a cylinder, and then offset it by one block, it'd be more like a corkscrew, right? You start at the top and it would spiral down. That's actually the way it should look, but that's kind of confusing to have on the wall. It'd be like a mobile. You have to spin it and stuff like that. So we'll handle that when we get to that point. So left of the stair step are metals, and hydrogen is the exception. Number 8. How can you experimentally determine whether a compound is ionic or covalent?
To see if it can conduct electricity.
Conduct electricity, and how would we actually do that? Yeah, it conducts electricity when? Are you just going to take it and stick electrodes in the powder and see what happens? It takes a lot of current to do that. It'll work, but it'll take a lot of current. It's true. Which one conducts? Ionic or covalent? Let's just start with that.
Ionic.
Ionic conduct. Because remember, what do ionic have in them? To be ionic, it has to have a metal, and metals conduct, right? So that's one way to help remember that. Ionics conduct because they have a metal, and the metals conduct. Well, it's not technically metals that are conducting here, it's the ions, and so the negative comes into play too. But the deal is, okay, so ionics conduct, but we generally think of them as conducting when dissolved in water. Because remember, water does not conduct. The only time water conducts electricity is when something is dissolved in it. And if that thing dissolved in it is ionic, it'll conduct electricity, close the circuit, and light bulb will go on. If it's covalent, it doesn't conduct electricity, and if there wasn't something already dissolved in that water, current won't pass and the light will not go on. Okay, that's the difference. So number 9, how can you determine from the periodic table whether a compound is ionic or covalent?
Where it lies on the jagged line.
So relative to the jagged line, right? So not on it, but relative to it, where does it lie? And if it lies on what? So relative where it lies, we just talked about it. So if it contains a metal, it'll conduct. So metals are to the left of the jagged line. Right? Number 10 says, which law governs how carbon and oxygen can form two different molecules, carbon monoxide and carbon dioxide?
I didn't do this one, but I understand it.
It's the law of multiple proportions. Okay? So we talked about Dalton and how Dalton explained conservation, explained definite proportion, and predicted multiple proportions because it said, you know, remember in our naming paradigms, we've got ionic names and covalent names. And which is more difficult? Which takes more thought process? Ionic or covalent? Louder? Covalent. Covalent has the prefixes, right? Di, tri, tetra. They have all those prefixes. Ionics don't. And ionics don't because they can only combine in one way. But in covalence, you take two elements, and they can come together to form a compound in multiple ways. Carbon monoxide is one carbon and one oxygen. Carbon dioxide is one carbon and two oxygen. If it was ionic, it would be either CO or CO2. It couldn't be either or. It would have to be one or the other. Okay? Because in the ionics, the metal and the nonmetals can only combine in a very particular formula, a very specific recipe. So I don't need to provide a lot more information. I can say sodium chloride. I don't have to say sodium monochloride. Why? Because sodium and chlorine can only combine as NaCl. They can't make Na2Cl, and they can't make NaCl2. They can only make NaCl. So when I say sodium chloride, you're, as a savvy scientist, go, sodium and chlorine? Oh, I know the formula. I can only do it this way. But if I say, I have a molecule here of carbon and oxygen, you're a savvy enough scientist to go, well, which molecule did you make? Because it can make more than one. It can make carbon monoxide, but it can also make carbon dioxide. You need more information. So that law that talks about how I can combine these molecules in different ways, the same two elements can form different compounds, is the law of multiple proportions. Number 11. And I just talked about it, so sorry about Stephen, but here we go. If you're 11, right?
Yeah.
Okay. So why do scientists use two different naming systems for compounds?
I don't think my answer's right. I'll say it anyways. Ionic compounds, there's like only one combination of atoms. And for covalent compounds, there's like many possible.
Yeah, same thing we just talked about. Right? The reason why we need two naming paradigms is we try to make it as simple as possible, and ionics are as simple as possible. But you know what? Not everything can be done simply because we need more information to be accurate, which is why we have a covalent paradigm as well. Number 12. If a substance can be physically separated into its components, is it a pure substance or a mixture?
Okay, so I wrote down the sentence that it was like in the book, and it was like, they can be physically separated, but the pure substance have to be decomposed. So,
Mm-hmm.
mixture?
So, okay, if a substance can be physically separated into its components, it's a mixture. Physically separated into its components. It means we're using a magnet, we're using a filter, we're using something mechanical that will physically do it, separate the pieces. Remember we talked about that mixture of sulfur and iron, and we put the magnet through it and all the iron went to the magnet? Okay, that's physically separating them, doing something mechanically, physically. Doing something chemically is different. So to say that I can't separate out a compound is not true, because if I take that compound and chemically decompose it, break it apart chemically, then I have elements, right? And by the nature of the atom within that element, I may be able to physically separate it. If we could reverse that sulfur-iron, the iron sulfide mixture, which is non-magnetic, if we could reverse the reaction and break it down back into iron and sulfur, then we could pass a magnet through and then it would separate. So that's what they were saying there. It's a mixture if you can physically separate it. It's a pure substance if you can't separate it. Oh, if you have a pure substance that's a compound, you can chemically separate it by decomposing it, and then maybe you can physically separate it when they're, individual atoms, individual elements made up of atoms. B. Or not. If a substance can be given a chemical name, such as calcium bromide, is it a pure substance or a mixture? Try again. Pure substance, right? If it has a chemical name, it's a pure substance. Which means if I have, in this case, calcium bromide, the example they gave us, it is a single named molecule. Every single molecule has the same exact construction. Everything looks exactly the same. If everything in the sample looks exactly the same, it's a pure substance. If anything in there is not the same, then it's a mixture. But if you can give it a name, which means every molecule is made up exactly the same combination of atoms, if they're all identical, then it's a pure substance. So before we talked about, remember, pure substances, we talked about the difference between an element and a compound. The atoms, actually, we have the elements and compounds made up of atoms and molecules. So element, compound, atoms, molecules. Those are all pure substances. Because whether it's an atom or a molecule made up of specific atoms, those are pure. Unless they're with other atoms. Like I can have a pure sample of, use the same example, pure sample of sulfur, a pure sample of iron, and I go mix them together, and I go, is it pure or is it a mixture? Well, it's a mixture. I just saw you mix it. Yeah, same concept. Do I want to make it pure again? Yeah. How do we do it? Physically separate it. I take the sulfur and iron, and I react it using heat, iron sulfide. Pure substance or mixture? It's a pure substance, because every piece of that mixture bonded by a certain way, so now it's a pure substance. I can break it down again if I can decompose it, but I can't physically separate it because it's a pure substance. Okay. So iron, sulfur, pure substances. Put them together, mixture. React it to form a new molecule, and they all react to make a new molecule, pure substance now. Because it's no longer sulfur, it's no longer iron, it's now iron sulfide. So if it has a single chemical name, it has a very discrete formula, a recipe, which means they're all the same, which means it's a pure substance. 14, the element that makes up the majority of the air we inhale. Nitrogen. You know it as chemical symbol N, but it actually exists as a homonuclear diatomic, which means it's an N2 molecule, not an N atom. But we'll get into that. So just to know it's nitrogen, that's fine. That's why I say right now in the early stages of chemistry, a lot of times you're writing something, and you might write N where it's supposed to be N2. And that's why when we do some of the reactions, you'll say, well, why do you have N subscript 2 up there when it says you add nitrogen and oxygen? Nitrogen doesn't exist as a single atom. It always bonds to other nitrogens to form the molecule of N2. But again, you'll see the N and go, oh, that's nitrogen. I don't understand why it has a subscript 2. That's fine for now. Later on, that'll be something where you write down N without the 2, and it's like, okay, that's wrong. Because nitrogen in the air isn't here as pure, is not the pure element N. You could have the molecule N2 for nitrogen. Same thing with oxygen. Oxygen isn't in the room right now in the form of O, elements of oxygen. It's actually in the form of molecules of O2, because oxygens bind with oxygens to form a molecule of O2. And 15, describe the difference between a quantitative and a qualitative measurement. One of my favorite questions.
Quantitative measurement is numerical. Qualitative measurement is non-numerical.
Okay.
That's all I could find.
Where was the answer to that at?
I had to Google it because I couldn't find it in the book.
Okay.
Ask Alex, she told me to Google it.
Pardon? Did anybody find it in the text? Where did you find it?
So it's like one of the experiments.
It's in the lab. Yeah, it's in the experiment. And it said, put approximately 25 milliliters or something. I believe that's what it was. Put approximately 25 milliliters into this. Quote, this is a qualitative measurement. See, qualitative and quantitative, and it's part of the work I'm doing in my doctorate, is used in research in other ways. But the core point is this. A quantitative measurement for chemistry, for you, that means getting it as exact as possible. Quantitatively means they want 25 milliliters, you're trying to give them 25.00 milliliters, okay? An actual quantitative number, a quantity. If you think about qualitative is more generalized. Put about 50 milliliters in there, okay? It's an approximation. In other words, if I'm putting in 50 mil, quantitatively, I'm trying to get exactly 50 mil, and I'm going to record if I'm off, so it affects my reaction, okay? If it says put about 50 milliliters in or 50 mil qualitatively, I'm going to pour it and try to stop at 50, but if I'm at 51, 52, 48 ballpark, it's fine. That's a qualitative measurement. Quantitative, specific. Qualitative, general. Now, that doesn't mean you go ahead and put 75 or 100 in. You know, get in the ballpark, but precision of your measurement at that point is not the issue. It's approximate amount. So if you want to think about quantitative exact, qualitative approximate, that'll work for now. Okay? We have more. Forgot, this is rather long. Number 16, a change that seems to break a molecule apart is called a chemical reaction, right? And we've talked specifically about breaking up a molecule, and it is called, what kind of reaction is it? We've talked about it enough that we're going to learn the different kinds of reactions, but we've already learned that this kind of reaction that breaks things down in chemistry is known as a decomposition reaction, right? We're going to decompose, not into gooey gook, but into individual elements. 17, a student writes the formula for sodium chloride as NaCl, and you got to look at it in the book. What is wrong with this formula?
L is capitalized.
And? Go ahead. Okay, so both of them, right? Both the A and the L should be lowercase. If I look at this NaCl, and I'm not savvy enough, but I know how chemistry is supposed to be written, I'm looking for the element N, the element A, the element C, and the element L. Now there is no element A. I don't believe there's an element L. So you've got me on a rabbit hunt if you said NaCl, N, capital N, lowercase a, capital C, lowercase l, that's two elements, the element Na and the element Cl. So what are the elements that lie along the jagged line called? Who's got the container? Metalloids, right, because they're on that line that separate metals from nonmetals, and so you're kind of saying, which one are you? Well, they're close enough that sometimes they act confused. So they're metalloids. But for this class, we're going to determine they're either metal or nonmetal, and just go with that for now. What is a dimensionless quantity? What does it mean if it's dimensionless?
But there's like, okay, after a dimensionless quantity is pretty much just quantity dimensionable. All the units cancel out.
That's the point. All the units cancel out, so it has no units. It's a dimensionless quantity because it has no units. Now, we said in here earlier that if it has a coefficient, a number with no units, generally speaking, it's wrong. It's going to be wrong most of the time. But we've got an exception now with the practice problems we're doing because we have multiples. Like, remember, we figure out how many batches we want to make? 6 batches, 7 batches. How many times do we need it? So when you do math and you've got units in the numerator and units in the denominator, and they perfectly cancel each other out, you get a number with no units. That is a dimensionless quantity. The derived unit for that is no unit. And number 20. Why doesn't distilled water conduct electricity?
I don't know if this is right or not, but 99% of all molecules in distilled water are H2O molecules. If they were all H2O molecules, it would be a pure substance, but it's a mixture, it cannot conduct electricity.
Wow. The short answer is there's no particles, there's no charged particles in it. Okay? So in pure H2O, the molecules are all together, H2O. There's nothing. See, for something to conduct electricity, when you put it in water, they have to separate out. When you put sodium chloride in water, what happens is the sodium ions and the chlorine ions come apart. And because those ions are apart, they can conduct electricity. Okay? If we put sodium chloride in water and it stayed NaCl bounded together, it wouldn't conduct electricity. But the fact that it comes apart means that it does. So that's the short answer. All right.